Hello everyone, I hope you're doing well. In this video, we'll be talking about the Feynman rules in quantum electrodynamics. Well, this is the part 2 of this video. In this video, we'll be seeing the rule 3 and rule 4, which are even more important than rule 1 and 2, but all of them are equally important. So let's quickly get started. In this way, we have satisfied and followed two of the rules in Feynman rules. And we'll refer to this diagram again and again, as I told you people that this is the foundation of all the calculations that we'll be doing later on. This is the second rule. Now the third rule is to write down the amplitude function. And for writing down the amplitude function, there are three factors that we need to incorporate, as I told you people, that we have vertices. So there will be a vertex factor. It's a mathematical quantity. We'll write it down. So first thing that we need to know is vertex factor, that will incorporate what's going on in these vertices. Then we have the propagator factor, that will incorporate the propagator that is involved in the Feyman diagram. And the last is the wave function for the external lines. We'll write down the wave function for the external lines, which are actually these wave functions. They will be multiplied in a specific order. We'll see it later. So there are three basically factors that are involved in the amplitude of the interaction. So we'll do it separately for the first diagram and then for the second diagram. And in the fourth step, we'll see how to add them up in. So the third step is to write down the amplitude function for each of these figures separately. We'll do it for this one first, then for this one secondly, and that's the third rule or step. Okay, so for that purpose, we first should know what are the vertex vector, what are the propagators, and yes, okay. So stay with me. I hope it's clear so far. What are we doing? We first draw the Feynman diagram. We labeled it. We understood each of their wave functions, their arrows, what they are telling us, how to decide what arrow's direction would be. We draw two possible Feynman diagrams and we label the momentum, which is the second step, and we understood that what does this arrow means. So that's all for the second step. Now let's move to the third step, which is to determine the factors on which the interaction amplitude depends. So we can write rule number 3. The amplitude depends on first is vertex factor, second is propagators. For internal lines means the mediating particles involved, and third is the wave functions for the external lines. External lines are actually the incoming and outgoing particles or whatever it is. So these are the three critical factors that are involved in writing down the amplitude function. So first we should know that what they are in general, and then we'll write down the amplitude function for the interaction that we are studying in here. Let's write down what is the vertex factor. Just understand them first, then we'll apply them. Like, we'll understand how to apply this knowledge and determine the scattering. Always I'm saying the scattering amplitude, it's interaction amplitude. Scattering is a specific kind of phenomena, so interaction is a better word to general broader word. So vertex factor, every QED vertex, vertex, whatever QED process you are studying, we have vertices in here. So for each vertex contributes a factor of iota G with subscript E. It incorporates the electron part times gamma, which is actually the propagator that is involved. Our mu on them, which shows that this is this propagator is linked to photon. Okay, we can see here that it is linked to electron, and that mu shows photon part, so that is linked to photon. We'll see we can for vertex A it will be mu here, for the vertex B it will be V here, that links to the outgoing positron, because that here what happened is that the photon was emitted at vertex A and photon was absorbed, this photon was absorbed by positron at vertex B. So there will be a difference depending upon which vertex you are seeing. So but in general we can write it like that: for incoming no, we don't need to do that, we'll see it later. So this is it, this is the vertex vector in general. And GE is a constant, is a dimensionless constant, is related to fine structure constant, where GE is a dimensionless constant and it is related to fine structure constant. And this fine structure constant is alpha equals GE squared by 4 pi. This is how the GE factor is related to fine structure constant, and we can see GE is a constant. Okay, just to know that what is GE actually. So this is the vertex vector. We have two vertices, so we'll have two vertex vectors and we'll change it accordingly depending upon what is the function, what is happening at the vertex. Okay, as I told you, where the emission is occurring, so it's gamma mu. Where absorption is occurring, we'll replace it with gamma mu, which is V. Maybe I'm V or mu. It's for like positron is absorbing that virtual photon. So we'll change it accordingly, but for now you just need to write it generally. All right. Yes, this is the vertex vector. Now let's write about the propagator, which is the next thing. Propagators. We can have photon propagator or we can have a particle propagator, because sometimes a virtual particle is emitted. So we have expression for propagator when it's a photon and a different expression for propagator when it's a particle propagator. Okay, it depends upon the type of interaction we'll have. Just as a vertex factor, we also have a propagator factor. Okay, so each internal line or photon that is involved connects, these propagators actually connects the vertices, of the form. We have two vertices, one has this vertex vector gamma mu where the emission is occurring, and another vertex vector in which the emission in absorption is having by positron. So like that. Okay, so we should expect the photon propagator to contract or connect the indices mu and v. Okay, since the propagator is connecting these two vertices, okay, mu and v, so we should expect the photon propagator should connect mu and v as well. As we can see, they are connecting the absorption and emission part, emission of photon, absorption by positron, so they should connect with each other. And photon propagator factor is actually minus iota g mu v, okay, divided by q square. We'll see what is q, and that's what the photon propagator did. They created a change in momentum. And yes, this is the photon propagator. Now a fermion propagator, if we have a fermion propagator, sometimes electron serves the purpose, like sometimes electron is a virtual propagator. So this also happens. And if there is a fermion propagator, this is the expression that you are supposed to use: iota phi plus m divided by q square minus m square. Okay, the sign of q matters. The sign of q changes actually depending upon matters here. We take it to be the same, to be in the same direction as the fermion arrows. We'll see it, we'll be using all of them, so we'll see when the sign will change. Okay, we'll see when it's minus q square or whatever, we'll do that. So this is the propagator, the second thing. Now the third thing is the external lines. The wave functions of external lines are represented in the Feynman diagrams. Figure 1 and 2. Okay, we know that. We can write it even here, we can draw the table right here to show that we have u bar, v bar, e mu, epsilon star mu to show the incoming and outgoing particles. So these wave functions for each half process work backwards along every fermion line. Work backwards along every fermion lines. What does that line means? We'll understand it like whenever we are writing the half process, we will write in an order that goes against these arrow lines. Okay, we can see there, these are the fermion lines and they are saying work backward along every fermion line, which means we'll move against these fermion lines. So they are linking with each other, so that will be one half process. We'll write its wave function first, then vertex vector, then its wave function first. But here we can see this arrow is downward, so we'll move upward against the arrow lines. Okay, what we have to do is to write down against the arrow lines. The arrow is actually in this direction, so we'll move and write down in this order. Okay, we'll write this one first and then this one and vertex vector in between. So that is what the working backwards mean. There is also a difference that comes along when we are considering the horizontal Feynman diagrams and vertical Feynman diagrams. We'll see them later on when we'll be finding them. So for now, let's find out the matrix element of 1, which is actually the product for the half processes, and then we'll be able to find out the matrix element 2, which is actually leading us ultimately towards the amplitude function. So let's do that for the figure 1 first, and then we'll be doing it for the figure 2 because both of them are involved. And matrix element 1. For that purpose, I'm going to draw the half process first, then we'll complete it as we go along. So this is the vertex and this is the emitted photon, and we have P1 and u of 1, and then we have u bar of 3 and P3. All right, and then after that we have this vertex 2, and we'll be drawing it later on when we have written the matrix element for this half process. So let's write it down. As I told you earlier that we have to move backward to the fermion line. Fermion line is moving in this direction from this to this, so we'll write it from opposite direction from this to this. So u bar of 3 first, u bar of 3 first. Okay, then the vertex first is the external line, which is u bar of 3, its wave function. Then comes the vertex vector, and vertex vector is minus, it's minus, yeah, no, it's plus iota G and subscript is E. Then we have gamma and mu over it, since it's a emission vertex. That is why mu over gamma. And then we have this from vertex, then we'll have this external line which is u of 1. Okay, and after that we'll have this propagator. We incorporated this half process, then we have this propagator that links this vertex with this vertex. So this linking factor in here, and what does that factor is, it's minus iota g, and we have in subscript mu and v. Here we have the mu on superscript, here we have mu v in the subscript, keep that in mind. And then we have q square. Q square is actually the difference in momentum that happened between the particle due to the emission of photon. Okay, and we can see that which particles actually witnessed the difference in the difference in momentum, due to which of them are involved in this emission. These two are involved. So difference in momentum of this particle and this particle is what the q square here means. Okay, so we have p1 minus p3. p1 is the initial momentum and p3 is the final momentum in its whole square. Okay, that is a propagator factor. All right, I hope it's clear to you. First you'll write the half process, we write it down, external line wave function, then vertex vector, external line wave function, then propagator, which will link it to another product of half process which is happening at the vertex 2. So let's draw it also. We have like that thing, and it's a v of 4 and p4, and here we have v bar of 2 and p2. Yes, that's all we need. And this is the vertex, let's call it as b, and this is vertex a. And let's write down the matrix element for this half process. So we'll move backward. The arrow is in this direction, you can see the arrow is downward, so we'll move upward direction. So we'll write this one first and vertex vector, and this one next. Okay, so it's always depending upon the fermion arrows. We'll write the mathematical form backwards. So it's v bar of 2 first, vertex vector then vertex vector ge gamma and mu this time because positron is absorbing it, and then we have v of 4, and propagator is already incorporated here, so we don't need to do this. So that is all the matrix element first for the figure 1. All right, and we can see that we wrote this factor first, this first, and then this. Okay, in vertical Feyman diagram we have some different things. So let's write it down, the matrix element 1 for the vertical diagram. And we have this thing first. So it's electron out, positron out. Yes, this is v of 4, and this is u bar of 3, this is p3, this is p4, this is one of the vertex, and then we have electron in, positron in, annihilation at this point, v bar of 2, p2, and u of 1 and p1. All right, and here what's gonna happen is that we'll write this process first, then this process. That's the difference between the vertical Feynman diagrams and horizontal Feynman diagrams, and you'll see this thing happening in every diagram. You will be encountering later on, we'll be doing some examples as well, you'll see the difference. So it's always happening, it's a general rule. So whenever you have horizontal Feynman diagrams, you'll write the factor for this one first and for this one secondly, and but in the vertical Feynman diagrams, you'll write the factor for the upward part first, then for the downward part. Okay, so let's do it for this vertical Feynman diagram. Let's write down the matrix element for this one, and while the propagator obviously will be written based on this thing. So let's write down the matrix element 1 for this one thing. And what is the direction of arrow? We can see here that arrow is moving in this direction from this to this. So we'll write the element, the product, from here to here, okay, opposite to the direction of arrow. Arrow is moving here from here to here, so we'll write from here to here, okay. U bar of 3 first, then this vertex factor, okay, and this vertex factor is iota g gamma mu here for this vertex, and then we have v of 4, okay. Since here we have creation of electron hole pair from a photon, so it's gamma, it's mu over there. Then we can have a propagator. We can write it with this factor as well, and like there as well. So let's write down the propagator separately, and we'll have minus iota g mu v divided by, here we can see here that the electron and positron combined together to form a photon, so their momentums will be added. All right, their momentum will be added because they combined to form a photon, while in this case the momentum changed because a photon was emitted out of this electron. So that is why momentum was carried away by photon, hence the momentum difference was encountered. But here they combine together, so their momentum will be added. So it will be p1 plus p2, p1 plus p2 whole square as propagator in this situation. All right, and lastly we have this matrix element, this one. So let's write it down. We will move against the arrow sign, so arrows are here in this direction from this to this, so we'll write from this to this. So v bar of 2 first, then we have vertex vector here. This is vertex vector, which is iota g e mu or gamma mu, okay, and we have this wave function u of 1 then. All right, so that is the matrix element 1 for these two diagrams. This is figure 2. Now let's write down the matrix element 2, which is actually the product of these currents, okay. Current at this vertex A and current at vertex B. We also call them as currents, or the interactions factors that are happening at both of these vertices. So the matrix element 2 is actually the product of these two. First this quantity and then this quantity, product of both of these quantities, and separately product of both of these quantities for the figure 2. Let's do that. The matrix element or the amplitude is proportional to the product of two currents or factors or contributions in the Feyman diagrams, figure 1 and figure 2. So let's write down the matrix element 1 for the figure 1. For figure 1, the matrix element is actually the product, so we simply write them together here. Iota g e gamma mu u of 1, then we have propagator minus iota g mu v in subscript, and p1 minus p3 whole square. Then we have v bar of 2, which is the second contribution, iota g e gamma mu and v of 4. Okay, that is the matrix element for the first figure. And for the second figure, we'll write them together as well. So we'll have u bar of 3, iota g e gamma mu v of 4, and then we have minus iota g mu v in subscript, then p1 plus p2 whole squared, and v bar of 2, then iota g e gamma v mu, and u of 1. Well, we have calculated the matrix elements, which was the crucial point. And first we draw the Feynman diagrams, we labeled it, and then we find out the matrix elements. And now it's the step to find out the scattering amplitude, okay, oh, interaction amplitude, and that is obtained. Let's see that how we can do that. Step 4, or we can say the rule number 4. Find the interaction amplitude for each Feynman diagram. We'll see, we just need to multiply iota with these quantities, and we'll get the amplitude for each of these Feynman diagrams. Okay, we'll get the amplitude for each of these Feynman diagrams. We just need to multiply iota, so we'll get m1, and this will be the m2. Find the interaction amplitude for each Feynman diagram. We will do that, and the overall amplitude, the net amplitude of the interaction is coherent sum of individual amplitudes. Okay, we'll add them together, individual amplitudes of each Feynman diagram. And while adding them together, we need to see one thing which is called as anti-symmetrization, and depending upon anti-symmetrization, there will be introduction of plus sign or minus sign. Okay, we'll see how to determine it. So that anti-symmetrization also applies here in step 4. That will determine whether it will be m1 plus m2 or m1 minus m2. It depends. Okay, so we will learn it right now. We'll see what applies in our case. So actually net amplitude is equals to m1 plus m2 plus m3 plus up to so on, but how, depending upon how many Feynman diagrams you have. For the process, we have 2 Feynman diagrams, so we'll stop our m2, but just in case you have greater number of them, so, and their square of amplitude is actually gives the physical results, because it will be a real quantity. And yes, you'll write it, just write it. And now let's write down the anti-symmetrization, and we are writing it down. We'll understand how it works obviously when we'll be dealing our example that we are having. It's part of anti-symmetrization. It's part of rule number 4. Include a minus sign between diagrams when they differ only in the exchange of 2 identical fermions. What does that mean? It means that if this is the diagram, if I want to convert, if this diagram could be converted into this diagram by just replacing a fermion, okay, 2 fermions, by replacing 2 fermions position, if this diagram could be converted into this diagram by just exchange of fermions, 2 fermions obviously, so we'll include a negative sign because we have the anti-symmetrization case in here. So here what happens is that, let's say this is positron here, this is electron here, okay, whereas here it was electron and here it was also electron. So we can see here that there used to be an electron over here, but it's positron over here. They are interacting with each other to give a photon, okay, but here what's happening is that a different situation, but electron is here nearer to that incoming electron. So what I can do to convert this figure into this is to, if I take this positron and make it here and take this electron here, if electron is here and positron is here, then we'll get the similar diagram. Okay, this is anti-symmetrization. Like if I exchange one fermion with another fermion, one fermion with another, I get the same result. Okay, if I exchange one of the particle, I'm getting the same result. Okay, if I take electron in here and positron in here, this diagram is essentially this diagram. Okay, because two electron cannot annihilate with each other to give a virtual photon. So the only valid reason to justify this Feyman diagram is that this electron emitted a virtual photon and become a outgoing electron. That's the only valid justification. So that is how one diagram could be converted into another by just replacing a identical fermion. This is how the situation could, work. Hence, in our case, the case that we have in here, we'll include a negative sign. Okay, it will be m1 minus m2. This will be m1 and this will be minus m2. And we'll have a case in Compton scattering. We'll understand it that in Compton scattering, there is no anti-symmetrization. So it will be m1 plus m2 in that case, and we'll see how. Okay, we'll see the exchange of particles doesn't bring any the exchange of similar fermions does not bring any difference to the diagram. Okay, and this is anti-symmetrization is actually related to Pauli exclusion principle as well. So we know that they the anti-symmetric nature of them. If you replace a fermion from x1 to x2, so its wave function would be inverted, like it will be negative of what it was before. But in case of bosons, there is no anti-symmetrization. If you replace x1 photon with x2 photon, there is no difference in wave function. But in case of fermions, if you replace a fermion from one position to another position, the wave functions are inverted. That is what is happening in here. If I replace the position of this electron with this position, this is x1 position and this is x2 position. If I replace electron from x2 position to x1 position, and similarly what was here to from x1 to x2, so what happens is that I'm getting this similar diagram. Okay, it means they are anti-symmetric to each other. All right, they are anti-symmetric to each other, and it's just like it's psi of x here. So this wave function is actually a negative of it. They are similar but negative in sign because they are obtained by just changing the position of particles or fermion particles in here. So that is what we are meaning in here. We'll understand it more in depth when we'll be solving the problem, because the thorough explanation and understanding comes when we are dealing with the problems, and we'll see and justify each and everything. So the clarification, the deeper clarification will come from the practicing. And yes, so let's do that. We had m equals now m1 minus m2. Okay, we can write here, since figure 1 and figure 2 differ only by a exchange of an electron of an what electron it was, outgoing electron, exchange of outgoing electron with incoming positron. Hence a minus sign will be introduced between the diagrams. and their scattering amplitude and their interaction amplitude. Okay, so let's have this situation now. M equals m1 minus m2. Okay, and here m1 is actually iota times, let me see what it was. Yes, iota times, we'll write m1, which is u, this is m1, u bar of 3 iota ge gamma mu u of 1 minus iota g mu v, and p1 minus p3 whole square, and v bar of t, I'm continuing the factor right here, they are gamma v of 4. Okay, this is m1. Now let's write m2. We can see it's a complex quantity, so it's square conjugate, it's a square modulus is actually a real quantity that will give us the real results. That is why we were taking the square of it in the previous expression that I wrote. Okay, just to make it a real quantity. 3. Then we have that ge gamma mu and v of 4, then propagator p1 plus p2 whole square. And let me know if the description that I'm having over here is enough for you people. If you, even if you want more in-depth description, let me know. I just don't know, I was just blank when this student told me to upload that video, because I don't know how much is enough and I'm trying my best. So m1 and m2, and capital M is actually this thing minus this this thing. Okay, so that is the scattering. Oh my god, why I'm not saying interaction amplitude. This gives the interaction amplitude for the interaction between electron and positron, as in accordance to the Feyman rules, and this is actually called as the Baba scattering. The interaction between electron and positron is called as Baba scattering. Oh, they are using the scattering word as well. So, well, you can use scattering as well for this. Okay, Baba scattering or Baba interaction. I don't know how to pronounce it. Okay, I'll see how to. But for now, forgive me. We can write the final expression by just putting the values into this expression, and we'll get the final result. All right, and in next video what I'm gonna do is to find out the same for the Compton scattering, and for different Mott scattering. We have different kind of scatterings in here, and we'll be doing it. Also there is there are matrices, S matrices that we know, and the S matrix expansion actually gives us the physical significance of all of these, and those S matrices actually help us to get these amplitudes, but they are so much lengthy and complex, you know. So Feynman rules are actually the shortcuts to get these results immediately, so that we don't have to do those complex and lengthy calculations every time. We can just follow the Feynman rules and we'll get the scattering amplitude expression. So Feynman rules make it a quick deal. S matrices are actually, we should know how to use S matrices and how they are telling us everything, because we should know every theory. But I'm just telling that S matrices are actually a bit more, you know, have more things to know. So let's do that. We can take iota as common. So we, well, u bar of 3 iota ge gamma mu in superscript u of 1, and then we have propagator minus iota g mu v by p1 minus p3 whole square, then v bar of 2, then iota g e gamma v, then v of 4, then comes the negative sign. Okay, you can write a little one. I'm just exaggerating its existence. So then we have this m2 factor. I took iota as common so that I don't have to write it again, but it's totally up to you if you want to write it separately or in one place. P1 plus P2 whole squared, and V bar of 2 iota GE gamma V and U of 1, and the bracket closes. This is the interaction amplitude. This is negative sign, okay? This is negative sign between them. That is the final. This is the interaction amplitude for Baba, for Baba. What kind of name it is for Baba scattering, which is actually the electron positron scattering. All right, and this is it for this video. I'll meet you in next video where we'll be practicing other examples, and we'll be finding out the scattering amplitude and interaction amplitude using the Feynman rules and Feynman diagrams. All right, so let me know if you want me to add some other things as well in it, or whatever you think about this video. I kept it as simple as possible and as detailed as possible so that you may know each and every detail. I suggest you people to practice this multiple times so that you get used to it, because there are so many things happening in here, so many new things which we are not comfortable with or we are not exposed to before. So yeah, that is it. Like, share and subscribe, and keep watching. Goodbye.